Hello, everyone, and hello, people online. It's my great honor to invite my colleague and also friend from University of Birmingham, and Dr. Marios. He's an associate professor in structural engineering at the University of Birmingham, and his main research includes the experimental and numerical research of structural steel, stainless steel, and also high-strength steel structures. And he has many years expertise in structural steel response at different levels, cross-sectional level, member level, and also system levels. And he has received funding over 2 million as PI or co-I in several research projects funded by EPSRC, the Royal Society, and also industry, and has supervised 13 PhD students to completion. His research funding on local buckling of stainless steel cross-section has led to significant amendments of the relevant stainless steel standards limits and also the effective width equations in the European Code. So he is also the member of the editorial panel for the iStructure research journal Structures, and also the committee members in the structure use of aluminum. And it's my great honor to invite Marios to give us a talk and on the topic of the resilient steel frame structures using stainless steel connections. So let's welcome.
Thank you very much, Shank, for the kind introduction. Good afternoon, everyone. Thank you very much for being here. Today, I will present some findings from a recently completed EPSRC-funded project called RESIST, which was on enhancing the robustness of steel-framed structures using stainless steels in strategic locations in connections. Yes. Okay. Sorry about that. So I will start the presentation with an introduction to Project RESIST and the challenge of progressive collapse that it addresses. Then I will move on to a brief presentation on material properties of the stainless steel grades we have used, both under static and mainly under high strain rates. Then I will move on to the behavior of lap joints, behavior of T-stabs, then behavior of full-scale connections, and finally, some conclusions we have reached. So it is a project that was completed in December 2025, but still the dissemination of the findings has not been completed, and actually some of the work is still ongoing, particularly on the numerical side. So what we were trying to address was progressive collapse. Progressive collapse can be caused by a localized damage to a key structural component due to a number of reasons that can include fire, blast, impact loading, or any unforeseen or unknown hazard leading to a severe localized damage. As we can see in this figure, if a column loss happens, the beams converging to the segment of the column above the damaged column will be subjected to very high localized loads that will cause very high rotations to the connections and impose very high strength demands on the connections as well through large deformation of the remaining structure. The catenary reaction will develop in the beams, provided that there is sufficient stiffness in the remaining structure not to allow the ends of the beams to freely pull in, and provided the connections can accommodate both the high rotation demand and the high strength demand. So there will be very high strength and rotation capacity demands in the connections. So the project RESIST was born because we thought of using stainless steel, which is known for having very high ductility in places where we actually need that high ductility. Here we can see some experimental stress strain curves for a typical carbon steel coupon, which is, can you see? No, you can see my, you can see my cursor, which is the blue line, and some stainless steel specimens that have overall a lot more strain hardening, a lot higher ductility, and bear in mind we don't show the complete curve here. So stainless steel, some stainless steel grades can have strain at ultimate stress more than 50%, which is a lot more than what carbon steel can have. And they are better in terms of energy dissipation. So there are certain clear advantages under monotonic quasi-static loading. As part of the project, we wanted to see to which extent the same advantages are valid under high strain rate loadings, which can happen during an extreme event causing progressive collapse. Another point that we investigated was the behavior of stainless steel under elevated temperatures. So in case of a fire, stainless steel retains its strength and stiffness better than carbon steel at elevated temperatures. And here we can see a curve that was taken from Euro 3 Part 1, 2, which shows the retention of Young's modulus in this case by stainless steel being the dotted line and by carbon steel being the black line. So similarly for ultimate capacity as well, there is a very large temperature range over which stainless steel significantly outperforms carbon steel. So in case of a fire, the connections are expected to behave better. I would also like to draw your attention to that very limited part of the curve here, where we can see that for relatively low high temperatures, if I can say that, stainless steel loses a bit of strength and stiffness, a bit more than carbon steel. And you will see why this is important, because some of the findings we got are explained from that. So Project Resist was undertaken by 4 universities, University of Birmingham, Imperial College London, University of Southampton, and UCL. And we investigated the potential of using stainless steel at key locations in the connections. I will mainly present research findings from work package 1, which was on resistance of connection components under static and high strain rate loading. That was led by Professor Gardner from Imperial College with contributions from my research group at University of Birmingham. And work package 3, which was led by myself with contributions from Dr. Saida Afsan from University of Southampton and her research team. So we will mainly focus on material, behavior of material, behavior of lap joints, T-stubs, and full joints, full-scale joints. We initially considered 2 stainless steel grades, conventional 1.4307, which is 304L in the American designation of stainless steels, and a more novel nickel-free austenitic stainless steel grade, which is EN 1.4678, which has the commercial designation of H500. Here we can see the obtained stress strain curves for the 14678, the novel nickel-free stainless steel, and the more conventional austenitic stainless steel grade. We can see that for the conventional stainless steel grade, we have a remarkably high ductility, so the strain at ultimate is about 70%, the strain fracture even more. The more novel grade has a strain at ultimate of a bit under 50%, but it has a very high strength, so the ultimate tensile stress is just below 1000 megapascals, and the nominal yield strength is about 470 megapascals. So we conducted a number of tests on traditional dog bone shape coupons to obtain the stress strain curves. And we, or Imperial College, conducted a number of tests on specially built coupons to obtain the fracture characteristics under a range of stress triaxialities. So in addition to dog bone specimens, also plate specimens with a notch were tested, and also specimens like this one, which induces failure under shear, were tested. This allowed the calibration of a fracture model, which was used later on in the numerical modeling of the connection tests. So in addition to the tests under more static loading conditions, tests were also conducted at high strain rates, and here are the results for standard coupons. So for the novel H500 nickel-free stainless steel coupon, we can see that with increasing strain rate, So the black line corresponds, the black curve corresponds to quasi-static conditions. And then progressively, we increase the strain rate to 100% per second, then 10 times more than that, and so on, until 10,000% per second. And we can see with increasing strain rate, we get a reduction in ductility, so reduction in strain at ultimate stress, but a significant increase in the nominal yield and the ultimate tensile stress for very high strain rates. For the conventional stainless steel 304L, we get a more marked reduction in ductility. And from the obtained results, we were able to plot the dynamic increase factor, so basically normalizing the relevant material properties by the relevant properties under static or quasi-static loading conditions. We can see that in all cases, the nominal yield stress increases significantly with increasing strain rate. It can increase up to about 1.8 times. I should also point out the fact that the strain rate of 100, so 10,000% per second, up to that strain rate, tests were conducted in a conventional tensile machine, whereas for higher strain rate, a split Hopkinson bar test was used to find the material properties in compression, and that's why we obtained the effect on nominal yield stress, but not on ultimate stress, since under compression there is no ultimate stress. So we can see that the yield stress, as expected, and as happens as well with carbon steel, increases significantly with increasing strain rate. The ductility, which is the top right-hand side diagram, decreases for both grades under increasing strain rates. What was unexpected was that the ultimate tensile stress for moderately low strain rates initially decreases, and as we increase the strain rate close to 50 per second or 100 per second, we get an increase in ultimate tensile stress. But for strain rates in the order of 100% per second, we have consistently a small decrease in the ultimate tensile stress. The reason for that is that at that strain rate, due to plastic deformation, the generated heat leads to a small loss of the ultimate tensile stress. So the thermal effect overshadows the strain rate effect. Whereas for very high strain rate, the strain rate effect becomes more important. So moving on to the behavior of bolted lap joints, having obtained the material coupon, we proceeded to testing lap joints under various configurations and loading speeds. The setup is shown on this slide, and the employed instrumentation included mainly digital image correlation, which allowed us to record full field strains and strain rates. The main failure modes we were targeting were bearing or tear out failure and net section fracture. So we designed two overall configurations. The one with the 6 bolt holes is meant to cause net section fracture at either the 3rd or the 4th bolt hole, whereas the one with the 4 bolt holes is meant to cause failure in the last bolt hole, where we varied the E1, the end distance, to see the effect of that on the bearing resistance. So for all configurations, we tested both stainless steel grades, and we also tested conventional carbon steel S355 lap joints for benchmarking. The applied strain rates varied from quasi-static up to about 80% per second, which gave us, according to the material tests, the biggest detrimental effect in terms of reducing the ultimate capacity. Overall, we conducted a total of 20 tests under static, quasi-static loading conditions, and 25 tests under higher strain rate conditions. Initially, we were planning to do a total of 12. We ended up doing 45. And the reason for that is, as we went along, we found things that we were not expecting to find. Which brings me to the discussion on the failure modes. Here we can see typical failure modes on this slide. For specimens designed to fail by bearing, the distance of the center of the ball hole from the edge, E1, was varied. And as we increased E1, the bearing resistance was increasing. At some point, we shifted the failure mode from tear out to either shearing of the bolt or net section fracture. So at some point, bearing resistance was more than the net section fracture or the shear resistance of the bolt. These are the typical failure modes we obtained, which we were expecting, like net section fracture, tear out, bolt and shear, etc. And this is a failure mode we definitely were not expecting. And we couldn't have obtained that even if we wanted to. So what happened here is that we have fracture, which does not pass through the critical cross-section, through the cross-section with the smallest section area. And in fact, the fracture began from the outer sides of the specimen and slowly progressed towards the inner parts of the specimen. We termed this sort of fracture surface crack-induced fracture, and the reason for that was that the company that donated the specimens for the lap joints, they used shearing as a cutting method. So there was a lot of localized hardening and some micro cracks induced. For the 14307 specimens, that didn't lead to any reduction in ductility or strength. So we did afterwards test some water jet cut specimens and the response was identical. But for the novel material, the 14678, for the shear cut specimens, that's what we got. And that was also accompanied by a pronounced decrease in ultimate stress. So we got a tensile failure about 15% lower than the one we got for the water jet cut specimens. And that's also one of the reasons why we ended up doing more tests, because then we had to order additional specimens that were water jet cut. We did similar tests on both static and high strain rate lap joints. The strain rates did not affect significantly the obtained failure mode. The failure mode was more or less identical, but for higher strain rate, failure occurred at smaller overall deformations without affecting the failure mode. Here, we can see some selected results. On the left-hand side, we see the carbon steel specimens. So top left is net section fracture, bottom left is shear out at the ball hole, so like bearing failure. We can see that for carbon steel, with increasing strain rate, with increasing loading speed, we have higher yield, higher ultimate stress, and lower ductility. For the stainless steel specimens, for both grades considered, both the conventional and the nickel-free one, with increasing strain rate, we get a decrease in ductility, an increase in yield resistance, but also a slight decrease in the ultimate tensile stress, because the strain rate we induced was similar to the one from the material coupon test that gave us that corresponding drop in the ultimate stress. So we saw that there is a reduction in ductility for stainless steel lap joints as for carbon steel lap joints. The effect on reducing ductility of the strain rates is smaller for carbon steel than for stainless steel. Stainless steel specimens, even at high strain rates, still possess superior ductility than carbon steel specimens under quasi-static loading conditions. And the increased strain rates lead to a drop in strength for stainless steel in accordance with the observations at the material level. So we were testing more or less in this area. That was an applied strain rate. And we got a small decrease in the capacity of the connections in accordance to the reduction in the strength of the material. After we completed the tests, or actually during doing the tests, we also did some numerical modeling. So we developed and validated numerical models against the experimental results. The failure modes in all cases were perfectly replicated. On average, the net section fracture models overestimated the strength by about 2% with a small coefficient of variation of about 4%. And the bearing models overestimated the strength by about 5% with a coefficient of variation of 1.8%. Here we can see the experimental and the numerical curves for net section fracture, for bearing failure, and also under high strain rates. Overall, the agreement is not bad, which allowed us to proceed to parametric studies. So upon validating the model, we ran a total of 86 models in parametric studies for specimens failing in bearing, and 70 for specimens failing by net section fracture, both under static loads. The modeling for for high strain rates, it's still ongoing, so we haven't completed that. That's why I'm presenting only the results for static loading conditions. We varied the end distance as a function of the ball hole diameter from 0.8, which is below the allowed, what Eurocode allows, which is 1.2 is the minimum allowed, but we were doing research, so we wanted to see what's the effect of that. So we varied from 0.8 to 4, and the edge distance, so the distance from the edges perpendicular to the direction of the applied load, was varied between 0.8 and 3. We saw that in all cases, the design equations for net section fracture was very accurate. The shear cut plates, we did not manage, obviously, to replicate the results for 14678 because of the very complicated conditions close to the edges due to the localized hardening. So we validated the model only for water jet cut specimens. We found that the provisions for bearing resistance given in Eurocode are overly conservative, and we proposed a new design guidance, a new design curve, a new design equation that is shown by this red curve, which better fits the experimental and the numerical results. In the new equation we propose, there is only independency of the bearing coefficient on the end distance C1 and not on the edge distance. Now, for people familiar with carbon steel design, the previous version of Eurocode 3.18, the one dealing with design of connections, included dependency on both the end and the edge distance. The recently revised version removed the dependence on the edge distance, so there is no E2 dependence. For stainless steel, though, the newly revised version still retains the E2 dependence, and according to our research, we don't see a reason why that should be happening. So we're proposing that this should be removed. So our proposed equation gave a much better agreement with the obtained results, with a significant reduction in scatter from 12.6% in the current Eurocode version to 4.9% using our equations. So this was the part of the research dedicated to bolted lap joints. Now we will move on to T-stabs. We are moving on to T-stabs. So we tested 8 T-stab specimens in tension under static loading conditions, and then we tested some additional under high strain rate conditions. In all cases, we had what we call a hybrid T-stab, where the web was made of carbon steel, S355, and the flange was made of stainless steel of the 2 grades that we used. We also did some tests on benchmark T-stabs with carbon steel for both flange and the web. So the flanges were either S355 steel with 8 mm thickness for the benchmark specimens, 8 mm in 14307 stainless steel for the conventional stainless steel grade that we used, and 6 mm for the novel stainless steel grade. We used the welding electrode that was recommended by the company Outokumpu that donated the specimens. And in all cases, we used M16 bolts in 18 mm clearance holes. We used high strength bolts, either 10.9 for the carbon steel specimens or 109 Bumax for the hybrid T-stabs, which is an equivalent bolt grade to the high strength carbon steel bolt grade. So we tested in tension under both static and high strain rates. Here you can see the overall configuration that we used. The blue is the specimen we tested, and we connected that to the actuator and we applied tensile load. We used digital image correlation to record full field displacement and strains. The loading speeds in this case were increased from what we did before. So we went from 9.4 millimeters per minute for the quasi-static loading conditions to 475 millimeters per second to induce higher strain rates. And the corresponding strain rates that we measured using digital image correlation, they reached up to over 300% per second for the 475 millimeters per second loading speed. Here, hopefully it will play. It's a video of one of the faster tests that we conducted. Yes, it plays. So don't blink, and that's it. So from the point that the load started being applied until we got fracture, it was less than 0.2 seconds, about 0.18 seconds. To be honest, we wanted to apply similar loading speeds for the lap joints as well. The problem being that we were the first to use the actuator, so we were within the specifications of the actuator, but the technicians had never tested under high strain rates. So we told them what we wanted. They thought they were providing it. At the end of the day, when we went over the results, we saw that we wanted to apply a loading speed of 100, and we ended up with a loading speed of 10 millimeters per second. And unfortunately, it can happen. It's a learning curve. In hindsight, I would like to be able to proceed a bit slower so that we could go back and test additional specimens, but we were running out of time, so that's what we got at the end of the day. We only got decently high loading speeds for the distance. So the results, some selected results are shown here. We can see for, on the left-hand side, the conventional stainless steel. So the solid curve is the static curve, and the dotted curves correspond to a loading speed of 9.4 millimeters per second and 470 millimeters per second. And we can see that we have a significant increase in the yield stress for the higher strain rate, a decrease in ductility, and also a small decrease in the ultimate stress based on what we observed before about the stainless steel material response at high strain rates. For the novel 14678 material, we got very similar overall observations. So with increasing strain rate, nothing changes too much in the elastic range, but we get a smaller displacement at failure and a slightly drop in the overall strength. For the carbon steel specimen, something weird happened. So for the static case, everything proceeded smoothly. For the high-ish strain rate of 12 millimeters per second loading speed, we got an asymmetric failure mode where we got fracture on one side of the specimen, not on the weld, but right next to the weld. So for the hybrid welding, we didn't get any fracture. For the theoretically easier welding between the same material, we got a fracture in the heat-affected zone of the weld. Having seen that the bolts govern failure, the bolt behavior at high strain rates is important, and we also had to look into it. So both Imperial College and Southampton, with whom we closely collaborated, did independently tests. At Imperial College, they looked more into the bolt material behavior, so they extracted coupons from bolts, so the machine down bolts to extract coupons, and the dynamic increase factor at ultimate stress with increasing strain rate is positive in this case. So with increasing strain rate, we get an increase in the ultimate stress of the bolts. In Southampton, they tested bolt assembly. So they have this overall frame where they test the assembly of the whole bolt and the nut. And again, similar observations were made. The static response is the one with the dotted line, and with increasing loading speed, the bolts become stronger. And very similar overall dynamic increase factors were obtained in both cases for the same bolts. Now, having seen that the stainless steel has a negative strain rate effect for small strain rates, we talked with Southampton, who at that time had some additional specimens made of Lind duplex stainless steel grade from another project, and we said, why not test that as well? So they did, on top of our test, some additional tests on T-stabs made of Lind duplex stainless steel grade 14162 at high strain rates, and in that case, both the material has the expected strain rate, so increasing ultimate stress with increasing strain rate, And the T-stubs also show that with increasing strain rate, you can get a slight or a higher increase in strength. So we tested T-stubs both with negative and positive strain rate effects. Two bolt grades were considered in these additional 20 tests. The DX109, which is a high-strength stainless steel bolt, and an austenitic stainless steel bolt, A470, which has a theoretical ultimate stress of about 700 megapascal. In reality, it's a bit higher than that, more towards 800. And for the DX bolts, the ultimate stress was about 1,140, so about 14% higher than the nominal one. And also two bolt grades were considered, M16 and M20. So after doing the tests, numerical modeling was carried out, and the models were validated against results for both static and high loading rates for all the materials considered. We recently submitted a paper for the Lind duplex stainless steel bolts, which is currently under review, and another paper on the two austenitic grades that we tested. Overall, we managed to obtain a good agreement between the experiments and the numerical modeling. For our specimens, for the ones that we tested in Birmingham, we found that due to welding, there was some significant distortion in the vicinity of the welds. So we had that upwards flaring of the flanges, which, if not considered in the numerical model, significantly affects the initial stiffness. So the black line corresponds to the perfect idealized geometry of a perfectly flat flange. When we incorporated the measured distortion, which was fairly visible, that's why we measured in the first place, we got a much better agreement between the experimental and the numerical results. After obtaining a good agreement, we carried out parametric studies, and we varied the thickness of the plate and also the location of the bolts. And when we went to very thin plates, we shifted the failure mode from bolt fracture to fracture of the plate material at high deformations due to membrane action in the vicinity of the bolt hole. These are some low displacement curves. The blue line that seems to have a more gradual loss of strength corresponds to that failure mode where we have a slower loss of material with progressive fracture. When we have bolt fracture, the end of the response, the fracture is more abrupt. Based on the numerical and the experimental results we obtained, we assessed the design provisions of Eurocode 3.18 for plastic resistance of T-stubs. They were found to be overly conservative for both static and high strain rates. Similar observations we had made with my good friend and colleague, Dr. Yuan from University of Wuhan in 2020, where we proposed a slight modification that improves the results. Instead of using the 0.2% proof strength as a nominal yield strength for stainless steel, we propose to use the 3% proof strength. So the stress at which, upon unloading, we have 3% plastic deformation. And when we do that, we obtain much better results for both static and high strain rate results, provided we use the correct material properties for the high strain rate results. So provided we have a good predictive equation for the dynamic increase factor. So Eurocode is overly conservative with the proposal of using a higher proof strength. We get less conservatism and slight drop in coefficient of variation. So having looked in detail into detail for the components of lap joints and T-stubs, which are key components in all connections, we proceeded to doing full-scale connection tests. So we did a total of 20 tests in Birmingham, 9 under static conditions and 11 under high loading rate conditions. This is the overall setup we used. So we had a column that was basically connected to a sleeve that we had anchored to the strong floor of the lab, and a beam that was loaded at the end at about 1.4 meters with an actuator. We were able to apply loading speeds differing from quasi-static conditions up to about 400 millimeters per second, so the actuator would move downwards at 400 millimeters per second. We had a look into 3 connection types: a traditional end plate connection, where we have an end plate welded on the beam and that bolted on the column flange; double web clit connection, which is a conventional pinned connection, a nominally pinned connection; and we also had top and seat angle clit connections, with angle clits being bolted on the beam flange and the column flange. Here you can see the breakdown of the test, total of 20 tests, 9 under static conditions, 11 under high strain rate. I will present the results for the end plate connection tests, since I don't believe I have the time to present all of them. And also, we were unable at this point to process all of them, partly due to the war, because I had a postdoc that is currently in Iran, and we have lost contact with him since February. So everything takes a bit longer, but that's obviously not that's not the problem now. So we used identical material as before, and we used 3 different bolts. We used a DX109 bolt, so the high strength stainless steel bolt, and we used A480 bolts under 2 conditions, both fully threaded and partially threaded. And the reason for that is that the thread forming process causes an increase in ultimate strength in stainless steel bolts, and we can have a partially threaded bolt where you load it in tension, and instead of having failure in the thread region where you have a smaller cross-sectional area, you have failure in the shank region where you have a larger cross-sectional area, because the material there is weaker. You haven't strengthened it with the threads forming process. So for the full-scale connection specimens, we wanted to do 6 tests. 1 specimen was by mistake destroyed, so we didn't test. It was tested without wanting to test it. We got results for 5 of them, 3 under static loading conditions and 2 under high strain rate conditions. And let's move on to the failure modes, which is the more interesting part. So we obtained 2 distinct failure modes at ultimate: either weld fracture with significant bolt deformation, and these are the 2 specimens that failed by weld fracture with significant bolt deformation. I believe it's very clear that here the bolts were almost at the end of their capacity. Here you can see clear signs of searing of the bolt, so you have tension and shear in the bolt, and at the same time we got fracture of the weld. Now, we did not see any weld fracture for the hybrid T-stabs, where we had the exact same weld thickness and the exact same weld consumables, and actually the same welder did both. So this is the failure mode with weld fracture. In that case, it was asymmetric, so it started from one end and started progressing towards the other. For that specimen, for the 14678 specimen, it started in the middle and started progressing outwards. And the remaining 3 specimens failed with bolt fracture under tension and shear. You can see here that that happened for fully threaded bolts and partially threaded bolts as well. And also that happened under static conditions and under high loading speed conditions. By high loading speeds, in this case, we applied a loading speed of about 10 millimeters per second, if I remember correctly. For the top and seat angle connections, we reached up to 400 millimeters per second. So we found that with increased loading rate, the maximum strain rate we recorded using digital image correlation was 4% per second. In reality, it must have been a bit higher than that, because we could only see the side of the plate and we could see the strain through the thickness. That led to an increase in ultimate capacity of 15% and also significantly higher plastic resistance. So if you compare the 2 red curves, the dotted one, which is higher than the continuous one, is at high strain rates. And because of that, we have a significant increase in the yield and in the ultimate resistance of about 9% in ultimate resistance, 15% in yield. The partially threaded bolts had 6.5% higher capacity, despite having 28% higher cross-sectional area. And that is because of the thread-forming process causing enhanced material properties in the vicinity of the threads. Similar results were, the same conclusions were verified by strain measurements, where we can see that at high strain rates for the same strain, we got higher moments, because for the same strain, we got higher stress in the material. And the conclusions we reached was, first of all, if you have a ductility critical application, avoid welding. We did try to eliminate welding as a possible failure mode. We didn't want to go into the microstructural effects of welding in the vicinity of the material, and that's why we oversized the welds. Nonetheless, at high deformations, we did get, in some cases, weld fracture. Fully threaded A480 bolts led to slightly lower strength despite having 22% smaller area due to enhanced strength caused by the thread forming process. We saw that an increased overall strength in specimens failing by bolt fracture was obtained. So what we recommended was to avoid this sort of end plate connections for a number of reasons. One is that weld fracture is not very predictable at extreme events. It may be fine for normal applications where the design resistance depends on the plastic resistance of the joint. But in that case, we're talking about extremely high deformations. And the recommendation was to focus more on connections incorporating angle clits where everything is bolted, and we rely simply on contact between the various parts and tension and shear of the bolts, which is easier to control. So, having done tests on full-scale connections in Birmingham, at the same time in Southampton, our colleagues did some tests on top and seat clit connections. So we saw that the end plate connections don't work, and we said, don't bother with that. And it's also more expensive to fabricate. So let's do more tests on top and seat angle clit connections. So we had this setup where we had the connection between two beams and a short column, and the load was applied from above downwards, and the alpha frames provided lateral restraint. So at high deformations, we had membrane action developing in the beams. So with increasing deformations, the beams were also taking tension. So the connection was subjected to bending moment and shear, obviously, and tension. These are the drawings of what the connections looked like, and the instrumentation made use of both digital image correlation and strain gauges. Several strain gauges were used in the beams as well, because that was the way to see the strain. From that, we could get the stress and hence the tension force due to membrane action, due to catenary action in the beams. In all cases, bolt fracture governed failure. No angle clit fracture was observed. Finite element models were validated and parametric studies, some were completed, some are underway. The results verify that for a stainless steel specimen, we have higher strength and a bit higher deformation compared to a carbon steel specimen. Then something that was not part originally of the project, but with this project, as we went along, we discovered many things that we wanted to do. So we did some additional, some further work that I will show. So we did some numerical modeling and experimental tests on angle clits produced through different production routes. So we did focused work on top and seat angle clit connections, which showed the most promising enhancing robustness. So we investigated the effect of having hot rolled angle clits, laser welded angle clits, or cold form angle clits on the strength and the ductility of the connections at the component level here. And we could see here the comparison between laser welding and hot rolled specimens. We had a change in failure mode. So for hot roll specimens, we had at very high deformation fracture in the vicinity of the ball hole over here, whereas for laser welding, we had fracture in the vicinity of the weld. The conclusions we reached from the project is that stainless steel has significantly higher ductility than carbon steel under static conditions and under high strain rates, although that advantage diminishes a bit with strain rate. For austenitic stainless steels, high loading rates may reduce the strength due to heat generation during plastic deformation. So it is not safe to say just use the static material properties, because you may get a small reduction up to 6-7% in ultimate stress. The lean duplex grade that originally was not part of the project did not display that strain rate sensitivity. In fact, it became better at higher strain rates. Experimental and numerical results confirmed that under both static and high loading rates, current design provisions are overly conservative, and we suggested some improved design equations in recently submitted papers. And despite over-designing the welds, we did get weld fracture. And our recommendation is that if you have a ductility critical application, avoiding welding would be a good strategy. So I would like to acknowledge EPSRC for the grant on resist on resilient buildings using stainless steel, Outokumpu and Bumax for donation of plate material and bolt material respectively, my colleagues from UCL, Professor Gardner from Imperial College London, Dr. Afsan from University of Southampton, and my two postdocs at the project, Dr. Manuela Cabrera, who is now in the University of Glasgow, Dr. Mohammed Ali Madavipur, who is in Yazd University in Iran, and also a soon-to-be doctor, Mr. Weiran Lee, who is a PhD student at the University of Southampton. Thank you for your attention, and I'll be happy to take your questions.